So in this video, we're going to dive deeper into the fundamental theorem of calculus part 1. We're going to expand this to be with the chain rule. So let's go back to the fundamental theorem of calculus part 1. What did this say? It said that let f be continuous on the closed interval and define the antiderivative to equal the integral from a number to x, the variable there, of f of t dt, where t was that dummy variable. Then f is differentiable on the interval a to b, open interval, and then the derivative of the antiderivative happens to be the integrand, and all we do is we take that upper limit of integration and plug it in to my function, my dummy variable t, replace it with the x there, okay? Now, what we're going to do, instead of having an x, we're going to have some other function in terms of x, and we're going to end up applying the chain rule, okay? So instead of just having an x, we're going to have a function g of x. So maybe g of x is like x squared or whatever, okay? So it's just a function of x. So then what? The derivative, chain rule says I take the derivative of the outside, which is capital F is the outside. So I take the derivative of the outside here, and then I keep the inside input the same. And now once I've taken the derivative of the outside, I need to focus on what's on the inside, which is g of x. And so then I take the derivative of g of x. So that's the definition of the chain rule right here. F composed of g of x derivative is equal to f prime of g of x times g prime of x. So what are those pieces? Well, what do we know about capital F and little f here? If I take the derivative ddx of capital F, what do I get? The derivative of the integral, those cancel each other out, right? And so if this had been an x up here, then I would just have f of x. But it's not f of x, it's f of g of x. Okay, little f of, and then I input the g of x in there. Okay, so whatever's up here, that function there, goes into this argument here. But the chain rule says this: not only do I have this inputted in here, but I have the derivative of what I inputted multiplied here. So that's the chain rule for you. So in general, it's of this form. It's f of something where I have a constant down here at my lower limit of integration, and then my something goes in the upper right there, okay? And so if that something is not x, then when I take the derivative, I have to add in that f of something here times the derivative of that something, whatever that something is, okay? If it's just x, then the derivative of x with respect to x is just 1. So that's, technically everything's a chain rule, right? But if it's just x, that chain rule part goes away. All right, so giving you a concrete example here, because that might be a little abstract, let's take this right here. So what's different about this problem than another problem? In a previous problem, we would have had something like capital F of x equal integral 3 to x of 5 to the t dt, right? And so if I took the derivative of this, then that's equal to the derivative of the integral from 3 to x 5 of t dt, right? Well, the reason this is simple is because those two things match there. So literally you take the 5 and you replace the t with what goes up in here in this exponent, and I put the x there, and that's my final answer right there, okay? That's pretty simple. But the problem why this doesn't work anymore is we don't have these things matching. This is an x to the fourth. So we need to handle this with a chain rule. So the first part is still the same, okay? It's f it's f of g of x, so that g of x for this one is x to the fourth, but then I multiply by the derivative of x to the fourth, okay? So this equals 5 to the, well, what do we plug in? We plug in this variable part up here. So that's x to the fourth up there. Times what? The derivative of x to the fourth. What's the derivative of x to the fourth? 4 comes out front, 4, and then subtract 1 from 4 to the x to the 3. So multiply this by its derivative, 4x cubed. So my final answer, I just put this first, okay, and then so it's 4x cubed times 5 raised to the x to the fourth. Let's try another one. So the other scenario here, so this first one we have a number down here and then my variable up here. Remember, it needs to be in this form where we have a number down here and a variable up here, okay? So this one gives us a little bit of a problem because there's a variable down here and a variable up here. So how do you handle this scenario here? Okay, so in this scenario, we're going to need to take this integral and break it up into two. That way we can have the variable and then like a number and then the number and then this last ln x here, okay? So let's use that property. If you recall, you had like the integral from a to c of f. This is equal to the integral from a to b of f plus the integral from b to c of f, right? So as long as you stop and start at the same spot, then it doesn't matter if you split it up into 2 or 3 or 4 or how many integrals you need to, okay? The reason I split it up here at b is maybe I can turn this b into a constant, and then that way my little trick will apply where I have a constant down low and then a variable for the other one, okay? So let's show you how this works in practice for this example. So with this one here, I'm going to split it into 2, like I said, and I start at A and I finish at B. So I know before I do anything that it's going to start at e to the x and it's going to end at ln x here. I just got to figure out what I want to put in there. And so you just pick a number, whatever number works for you, okay, as long as you're continuous there. But guys, if you're continuous, if your function is continuous everywhere, then it doesn't matter what number you pick here, okay? So I picked the same number to match up, and so I finish it off. So I started here, I ended here, and then my numbers that match up are right here, okay? So this is equal to this original capital F of x. So now what I want to do is I want to take advantage of the properties, because now I've got like the opposite scenario going on. I've got the number divided by, and then the variable down here for this, and I want these to be swapped around. I wish there was a rule that allowed us to swap the limits of integration. Oh wait, there is, right? So I can swap the limit. Instead of starting with a equal to e to the x, I can swap it around and make it start at 0 and then end at e to the x. But if I do that, I pull out that negative factor, because remember that delta x turns negative on me. Okay, I end up doing left minus right instead of right minus left. And then here, this one is just fine. I have my variable up top and my number down here, like what I want there. Okay, so I don't have to do any magic math on that part. So now all I have to do is apply the fundamental theorem of calculus. Whenever I take the derivative of the integral, it goes away, and so I have a negative. And then I have cosine of, well, my dummy variable is t, so I'm going to plug in e to the x here. And then I need to multiply this whole function by the derivative of e to the x, because those don't match up there, okay? So the derivative of e to the x is e to the x. How about that? And then for this last one here, if I take the derivative of the integral goes away, and I plug in my dummy variable, I plug in that variable, that block that goes up in here, right? Okay? And so whenever I do that, I get ln x, cosine of ln x, and then times the derivative of the ln x. Remember, it's the chain rule going on. The derivative of ln x is 1 over x. Okay? So hopefully this kind of gives you a better idea of how the chain rule works here. This is meant to be some of the easiest problems in all of calculus. If you think about it, the derivative of the integral, so if you just have some number down here and x here, f of t dt, the derivative of the integral is just f of x, okay? Where it changes is when you're dealing with a situation where it's like the derivative of the integral and you got your number and it's like, you know, it's maybe it's, heck, I don't know, like x cubed, right? So now all of a sudden, and then it's your f of t dt, right? So the problem is this x doesn't match that x cubed. So you gotta take a chain rule into account here. And so first off, I replaced every t with an x cubed, just like I replaced every t with an x in this problem. So I plug in a x cubed here for my function, but then the chain rule says I need to take the derivative. I need to multiply this by the derivative, right? So I need to multiply this by the derivative of x cubed because it's the chain rule going on in here. And so this is f of x cubed times 3x squared. Okay? So your answer, 3x squared times f of x cubed. I just rewrote it in a different order there. All right? All right, hopefully